Please, Netta.
Okay. All right. Thank you for the invitation. So this talk is essentially about computing the free energy or the generating functional from the gravitational path integral. And to motivate this, and really at the end of the day, the contributions from replica wormholes. And to motivate this, I will begin by talking about the black hole information paradox, which will be the first, maybe 25% of the talk. Now, I should say this is based mostly on, well, there'll be a bit of a review on recent developments on the information paradox, but it'll mostly be based on the recent paper from last month, or I guess now it's July, so from July with Sebastian Fischetti and Alex Maloney. Next slide. Okay. So here I've drawn the canonical picture of the asymptotically flat evaporating black hole. And the past year has seen a lot of progress on the front of the black hole information paradox. Now, of course, the reason we are interested at the end of the day in the black hole information paradox is not for its own sake, but in order to understand quantum gravity better, since the paradox about quantum gravity is bound to teach us something about it. And one of the reasons I'm so thrilled about these recent developments is that they've lived up to that, in the sense that these new developments have started to teach us more about gravity in general. So this is a really exciting development, which it's nice that it's lived up to what we were hoping for so far. Now, there have been a number of insights, and I will not talk about all of them. I'm going to talk specifically about the inclusion of replica wormholes, these Euclidean wormholes in the replica trick, the gravitational replica trick for computing the von Neumann entropy of the Hawking radiation. And this is related to some older work on Euclidean wormholes and ensembles and gravity and the gravitational path integral. And it's really shed some interesting new light and has fueled a lot of interesting developments on these older insights about Euclidean wormholes. So I'm going to set the stage. I'm going to review first the initial developments that are really purely focused on the black hole information paradox, and then some of the later developments that have told us more about gravity, such as the inclusion of Euclidean wormholes in the gravitational path integral. And then I'm going to discuss this new work on replica wormholes with Sebastian Fischetti and Alex Maloney. So this is the outline. First, information paradox and the replica wormholes. Then I'm going to talk about how we compute the free energy in a way that will show us that replica wormholes contribute. And the way to do this is to do another replica trick, which is one that is frequently used in condensed matter, but somewhat rarely used in high energy theory. It's a distinct replica trick from the one that is used to compute the von Neumann entropy. And I will do the calculation explicitly, well, not in all gory detail, but somewhat explicitly in JT gravity, which is what we did in this paper, and show that there is a regime where the theory is under control, and these replica wormholes in this different replica trick do dominate, or at least their contributions are very important. And then I'll summarize and make some comments about future work. So I think no talk about the black hole information paradox is complete without at least a picture of the page curve. So let me begin with the page curve. The initial results that started all of this new developments, this exciting new results, have been a computation of the replica of the page curve in ADS-CFT, so a holographic calculation of the page curve. Now, the basic trick was to force an ADS black hole to evaporate. Large ADS black holes don't generally evaporate, but you can force it to evaporate by coupling it to an external reservoir at a lower temperature. And this forces the black hole to evaporate, and then you can use the holographic prescription for the von Neumann entropy with quantum corrections, the quantum extremal surface prescription from 2014 that results in a unitary page curve. So here I have the three different curves that we normally associate with black hole evaporation. We have the entropy of the radiation as computed by Hawking, which increases and then eventually saturates. We have the Bekenstein-Hawking entropy. This is just the area of the black hole. And finally, we have the unitary evolution of the entropy. So this essentially says that the entropy starts out, the state starts out as pure, and then eventually ends up as pure, the state of the radiation, say, so it better come down again. And there's a detailed analysis of this. There was a detailed analysis by Page, and we did a detailed analysis in these papers. So,
a quick comment about, yeah. So this page curve is observed by a semi-classical observer, meaning he doesn't have access to how many points.
sorry, you keep on getting cut off. Could you repeat that, or maybe type it into the chat?
Okay. Okay. So
sorry, you're keep on getting
chat.
cut off. Yeah.
Okay.
Sorry, if it's in the chat, I can't see it. Maybe.
Yeah. So maybe, like, yeah.
Somehow. Oh, I see. Okay. Somehow. Okay. Okay. So you're saying, is a page curve something that you can compute via semi-classical observables? That's a very good question. So I think many of us would have said, and certainly I would have said a couple of years ago, that in order to compute a unitary page curve, you need to have access to non-perturbative quantum gravity for sure. One of the most exciting aspects of these new developments is that if you can actually calculate this using purely semi-classical physics, as long as you are willing to buy the quantum extremal surface prescription. So you could say that there is a non-perturbative quantum gravity element here, in the sense that the quantum extremal surface prescription is a holographic prescription, and as such it incorporates non-perturbative quantum gravity. But the calculation itself, in the interpretation, you could say really requires holography, which is non-perturbative quantum gravity, but the calculation can be done purely semi-classically.
In the setup, I'm sorry for the interruption again. Am I audible?
Sorry, what was the question?
Yeah, so am I audible?
Yeah, now you are.
Okay, thank you. So in the setup, we have, so the page curve or the quantum extremal surface prescription seems to suggest that Hawking radiation is a non-local object, meaning we can't treat it like a local QFT. So the unitary page curve which we observe for a local QFP shouldn't necessarily be valid for Hawking radiation as observed by a semi-classical observer. It seems that replica trick is giving us the naive page curve, but is it necessary that replica is...
Sorry, James, sorry. Maybe, like, we can, like, proceed with the talk, and when these things come about, then you can ask your question. Because I think
yeah, sure. I'm sorry.
All right, I'll plow forward then. I will say that the page curve is not essential to this talk. It's more a motivational aspect, but you ask an interesting question, which I do have some things to say to, but I'll address it at the end. So let me just give a brief reminder of the quantum extremal surface prescription, since it's important for all of these developments. Essentially, it tells you that you can compute the von Neumann entropy of a density matrix rho sub R on the boundary. Here, R is meant to denote a boundary subregion, but it can also be the entire boundary, or both boundaries if you have multiple boundaries. So this is given by the area of a 4G H bar of some surface chi sub R, plus the von Neumann entropy on one side of the surface. Now, this quantity is in general called the generalized entropy, and the surface chi sub R is the minimal generalized entropy surface. In other words, the surface that extremizes S-gen. So in other words, if you take all surfaces that extremize this quantity, and you then ask for the one with the minimal S-gen, that is the surface whose generalized entropy computes the von Neumann entropy of a density matrix rho sub R. Now, here's a picture in the high dimensional case. So we have chi sub R, we have R, and this is this out. So we compute the von Neumann entropy of quantum states, of quantum fields here, and then we add it to the area of x sub R over 4G H bar, and we extremize over the location of the surface x sub R, or chi sub R. Now, I'm not going to spend too much time on these developments, but there's the main takeaway, which is important for the later developments. which is that the way that this actually, a new quantum extremal surface that nucleates, it doesn't have a classical counterpart. So here I've drawn a picture of a two-sided black hole in JT gravity. And what we've done is we've coupled the right side to an auxiliary reservoir. We've evaporated it into that reservoir. Chi sub L here, this is the original bifurcation surface, which is also the quantum extremal surface before the black hole has started evaporating, before we've coupled it, is the quantum extremal surface both for the left boundary and for the right boundary. At late times, what happens is that there's a new quantum extremal surface for the right boundary, chi sub R, which is very different from chi sub L. They are separated by a large distance, and it has no classical counterpart. Now I keep on harping on that. I just want to say how surprising that is. If you look at the formula for the quantum extremal surface, if you're working in perturbative quantum gravity, you would expect that this quantity here is always going to be subleading, that you're always going, it will be dominated by this, so that if you do some kind of a quantum corrected calculation, it might shift the quantum extremal surface from the classical one by some Planck length, but you wouldn't necessarily expect them to be so largely separated. And the thing to keep in mind here, of course, is that we're extremizing this quantity. So we're talking about gradients, and the gradients are certainly allowed to balance. And this is, in fact, what happens in this case over here. Chi sub R has these balancing gradients, so it is a quantum extremal surface, even though it has no classical counterpart near it. So the effect of this transition of this late time quantum extremal surface chi sub R nucleating and dominating is, in fact, the unitarity of the Page curve in the bulk. Now, this so far computes, I should say, this quantum extremal surface prescription is holographic, so it computes the entropy of the black hole. You'd like to also compute the entropy of the radiation. They should be the same, of course, but you won't need a prescription for that. And so you can generalize the quantum extremal surface to the non-gravitational region. So in other words, to the Hawking radiation, which has left the bulk and gone into the reservoir. And what this gives you is this formula here, which looks very similar to the generalized entropy, but it's slightly different in the sense that here we're going to be extremizing over all bulk regions I. We're going to be computing the von Neumann entropy of I plus the radiation. Here, this is meant to be a coarse-grained entropy in a sense, and this is meant to be in some sense a fine-grained entropy. And I should say that this type of formula was applied in somewhat less than explicitly, but it was applied in a similar context by Hayden Pennington. And it was afterwards more formalized into the so-called quantum extremal island formula by Almhairi, Mahajan, Molasena, Mahajan, and Zhao, where this here is the quantum extremal island. Now, this is a very nice, I should say, this is a very nice proposal. It gives us unitarity of the radiation, and it's something that we like a lot, but of course it's a proposal. And as a conjecture, we would like to find some way of justifying it. So this brought forward these new developments of the toy models in which this formula was justified in 2 dimensions. So there's the so-called East Coast model and the so-called West Coast model. I'm going to focus primarily on the East Coast model because it's more compatible with the free energy replica wormhole calculations. At least it's easier to see how they work there. So here we have the East Coast model takes this 2-dimensional ADS region, JT gravity in here, and it's in a very similar way to what was done in the Page curve calculations holographically. It has this flat region with no gravity that's coupled over here. The West Coast model is a little bit different. It has an end of the world brane here with a flavor index and an associated Hilbert space to that. Again, I'm going to focus on the East Coast model today. So essentially what these do is they give a derivation of the unitary Page curve and the quantum extremal island formula for the radiation in these toy models, where you have 2D gravity and JT gravity. And what they do is they use the gravitational replica trick. So you pick some region R over here. This is some subset of the radiation. And what you hope in doing this gravitational replica trick is that you would find this quantum extremal island over here. So let me just briefly review the von Neumann entropy replica trick, since it's going to be very important for the rest of the talk. So here we have the nth Renyi entropy of some density matrix rho sub R is defined in this way. And the von Neumann entropy can be computed by taking the n goes to 1 limit. This is something that we do a lot in gravity. Although I should say this is not, right now I haven't invoked gravity just yet. Now, I'm now going to switch to Euclidean signature, and in fact, the rest of this talk is all going to be in Euclidean signature. These pictures up here were all in Lorentzian signature, but I'm now going to switch completely and not talk about the Lorentzian picture again. So if we work in Euclidean signature, we can rewrite the state in terms of the Euclidean partition function, which gives us the following formula. Now, this z of b is a partition function on the whole space B, and z of b sub n is a partition function on B sub n, which is this n-sheeted geometry that consists of n copies of B that are cut along R. Again, this is rho sub R. These are cut along R and then cyclically identified along R. So this is the image that you often see that comes with this formula. So now let's put gravity back in. So the idea is that we replace, this is Lefkowitz-Moldesteiner, we replace z by the gravitational path integral. So we take z of b, replace it by p of b, that's my notation for the gravitational path integral, which is going to be just the gravitational path integral with boundary conditions b. And z of b sub n is replaced by the gravitational path integral p of b sub n, where again the boundary conditions are this n-sheeted cyclically identified manifold. Now, just as an aside, in the East Coast model, for example, the identified region R is not in the gravitational region. So the gravitational path integral is over n copies of the ADS boundary that are not identified. So in the figure, so here we have the ADS boundary, we have n copies of it, and then we have the identification out here. Now, let me sort of get to the crux of it. In general, the gravitational path integral on n copies of the boundary B is equal to the gravitational path integral on a single copy raised to the power n plus connected topologies. And it was subject of many papers, whether the connected topologies should be included or should not be included. So discussed in here, this is just a small selection of papers. Now, if we put aside these other considerations and we just say, well, we want unitarity, then it was found by both the East Coast and West Coast groups that after the page time, the contribution from connected topologies dominates. So this corresponds essentially, so here is what the so-called replica wormhole that connects these boundaries. And in fact, this contribution is what corresponds to the new quantum extremal surface or the quantum extremal Island formula and gives us this unitary page curve. Now, should these topologies be included? That's a really important question to ask. Now, these topologies result in a unitary page curve. So if that's all we're going by, then we say we would certainly like to include them. But if we include them, of course, it immediately means that p of b to the n is not the same as p of b raised to the power n. And so subsequently, if we say that the partition function is literally equal to the gravitational path integral, we have a factorization problem. Now, one possibility that has long been discussed in the literature for resolving this apparent problem is that the gravitational path integral doesn't compute an exact partition function, but rather an ensemble average. I'll put an aside in the next slide about that, but let me just talk about another couple of possibilities. There's also a possibility that there's some non-perturbative corrections that restore factorization. Maybe the gravitational path integral is just a really good tool for computing quantities that are self-averaging in a single chaotic theory. There are a number of different hypotheses on what it means that the gravitational path integral does not factorize. Now, I'm going to be agnostic about whether the gravitational path integral is ensemble averaging or not. I'm going to use the word an average just to denote what the gravitational path integral is doing, but it doesn't matter for me what is the exact mechanism that it's doing, what is the exact procedure that is implemented by the gravitational path integral. So let me just make a brief aside on the averaging, and then I'll move on to and be more agnostic about what it's actually doing. So normally what we mean by ensemble or disorder averaging is that the partition function is denoted by z sub g of b, where g is some coupling constants. It is defined with respect to some choice of coupling constants that are sampled from a distribution. And this average is given by integral against the distribution. Now, if this is what the gravitational path integral is computing in gravity, it's not obvious what an individual member of this ensemble is. I think this is a really important question. It's just an aside. I'm not going to subscribe to any particular interpretation of the gravitational path integral, but it's something that's very important to remember for those of us who do subscribe to it. Okay,
Can
so
I
now
have a quick question, please?
sorry, what was that?
Can I have a quick question?
Yeah.
So did you mean an average of the partition function or log of the partition function?
So I haven't talked about the log yet, and I will,
Oh.
that's a very important distinction that I will talk about. The next section will be all about the distinction between log of the average and average of the log.
Okay.
Yeah. All right, so a few questions. If we want to take these replica wormholes seriously, which we do because they give us unitarity, then we need to understand better what kind of calculation the gravitational path integral is doing. And if it's averaging, what is it averaging over? And perhaps maybe the easiest way to start asking these questions, start understanding what kind of calculation the gravitational path integral is doing, is to ask what are the implications for other observables? Can we see signatures of replica wormholes or whatever mechanism allows for replica wormholes to contribute beyond their any entropies? So for instance, we might ask about the generating functional log z, or equivalently the free energy minus T log z. And so now I'm finally getting to the replica trick for the free energy. Now, if the gravitational path integral receives contributions from connected topologies, then in principle, as we had literally just discussed in the question, there could be a big difference between log of the average of z, which is just log of the gravitational path integral, versus the average of log z. When I say average, I mean whatever the gravitational path integral is computing. Now, in condensed matter systems, this first one is called the annealed free energy, and it computes an average over the random variables that define a particular instance of the ensemble, which suggests that there is an interpretation as the generating functional in a theory in which the random variables are allowed to equilibrate. The second one is a quenched free energy, which computes an average over the free energies of the constituents of the ensemble. So this is literally an average of the log, where the random variables are not allowed to equilibrate. Now, again, I'm not going to subscribe to a particular interpretation of the gravitational path integral, but it seems that even if it's not computing an ensemble, it's pretty clear that what we care about is log z as computed by the gravitational path integral rather than log of z computed by the gravitational path integral. It seems clear that the quenched free energy is the one that we really care about. Now, of course, if the average of z of b to the n is not the same as the average of z of b raised to the power n, then we might also expect that the average of log z is not the same as log of the average of z. So how do we make sense of, how can we compute the average of log z purely from the gravitational path integral? And this is just the log z replica trick, which we, again, rarely use in high energy theory, but is very frequently used in condensed matter. And this is this rewriting of log z in this way. So it's just z of b to the m, and 1 over m times z of b to the n minus 1. Now, we take the limit as m goes to 0. So here we introduce m replicas, and we take the limit as m goes to 0. It's a somewhat different limit than the von Neumann entropy replica trick. Now, of course, z of b to the m is something that we can calculate. Its average is something we can calculate from the gravitational path integral. So we say, okay, the average of log z of b is just given by this replica trick with the gravitational path integral p of b to the m. Now,
Sorry,
yeah.
I just had a quick question. Can you comment more about the, there were two ways of computing the partition function, averaging the partition function and taking the partition function and then averaging it. I wasn't able to understand clearly the second formalism. It went really too quick. If you don't, can we revisit it?
Sorry, what is the question again?
Can we revisit the second formalism used for so it's ensemble averaging and averaging over ensemble? Can we revisit the second formalism that is averaging over the ensemble?
So you said a second formalism, you mean the quenched free energy?
Yeah, yeah.
Okay, so you're asking if what kind of averaging it's doing, or I mean, I'm not subscribing to any particular averaging so much as I'm saying, so let me go back one slide. So whatever the gravitational path integral is computing, that's what I'm denoting by an overbar here. And so whether it's an averaging or it's something else, the important point is that it appears that this quantity, or rather it is this quantity, which is computed by a replica trick, which is important to us. And if you doubt that, and you may not agree with me right now, you may say you're not sure, or maybe you think that we have to subscribe to an ensemble average interpretation in order to accept that. But if you hold on to that thought for maybe 10 minutes, then I'm going to give an example in JT gravity, where if you compute this quantity, you actually get a very unphysical and pathological answer. And it turns out you have to do this calculation instead. So if you can maybe hold on to skepticism for another 10 minutes, and I think I'll answer your question then, if I didn't answer it already.
It's really fast. I'm sorry.
So what was that? I'm sorry, you keep on getting cut off. Okay,
I'm just saying it's too fast.
I'm sorry, I'm going to move on because I can't, you keep on getting cut off. I can't hear what you're saying. Okay, so if replica wormholes can contribute non-trivially in this m goes to 0 limit, and again, this is an important part of it, then the quenched free energy is going to be very different from the annealed free energy. So this number here is going to be very different from this one. The reason being that this only receives contributions from disconnected topologies like this. And this one can, in principle, receive contributions from replica wormholes. So let me give you an example of actually a situation where it's important. We can already see, just at subleading order, I'll talk about leading order later, but at subleading order, we can already see why it's very important to include this replica trick. So suppose you want to compute the von Neumann entropy of a pure state. Or actually, let me take that back for a second. Suppose I want to compute the von Neumann entropy period, and we want to compute it using the gravitational path integral. Or really, in fact, any quantity we want to compute using the generating functional log z is going to receive this type of correction. But we're familiar with the von Neumann entropy, so let's go with that for now. So the von Neumann entropy is going to be given by this same replica trick that we know and love. And each one of these now has to have an additional replica trick in it to be computed properly using the gravitational path integral. So in other words, this has to be computed, to be consistent, has to be computed via a compounded doubled replica trick, where we encounter this funny geometry here, which is B sub n, this n-sheeted manifold, which is this thing over here, but m copies of it. So this geometry here is meant to be B sub n to the m copies of this n-sheeted periodically cyclically identified geometry. Okay, so now let's talk about the Renyi entropy of a pure state. So as von Neumann for rho here is a pure state. If we don't use the log z replica trick, then we find the following formula. We just have this annealed free energy here and also here. Now, if replica wormholes contribute at any...
Can I ask a question?
Please.
Yeah, so is there a calculation where you would need to include wormholes across the m copies in the n-sheeted, but across the m copies?
Yeah. Is the calculation, was it what?
Where I would need to include wormholes connecting across the m copies of the n-sheeted geometry.
So I haven't said anything about the replica wormholes in the M replica trick just yet. So maybe you can hold on to that question. I'm going to talk about, well, subleading order replica wormholes contributing to the von Neumann entropy for this, okay? And then I think maybe I might be able to answer that question better later on. So let's compute here the von Neumann entropy for a pure state. So if we don't use the log z replica trick, we're just using the annealed free energy here and here. Now the problem is, if replica wormholes contribute at any order, and doesn't have to be at leading order, it can be at subleading order, then this quantity is not going to vanish identically for a pure state. But if we use the log z replica trick, then for a pure state, we have b sub n to the m is just b n m. And so we can rewrite this in this way. And finally, what we get from that is something which is identically 0 to all orders, which is exactly what a pure state should be. So even though this appears to only fix a subleading order problem, it does seem that it's quite important to include this replica trick regardless. Now, subleading corrections are important, but they're not nearly as exciting as leading order corrections. So I do want to talk about leading order corrections to log z. Now, just for log z, we don't need this compounded replica trick. I introduced it mainly for intuition about what might happen if we don't include it in a quantity that we know and have calculated many times. But just for log z, we just need m copies. We don't need this mn geometry. Now, since we're working with ADS boundary conditions, so unlike the East Coast paper, we're not going to care about the flat region here. I'm going to draw these as ADS boundaries. Now, the question that we want to ask is really want to ask about leading order. So is there a simple theory of gravity where the theory is under good control, where replica wormholes actually contribute to log z at least as much as the disconnected topologies do? Now in JT gravity and also in some other cases, there have been a number of studies of the lack of factorization due to contributions of connected topologies to PB to the M. So obviously if you have the contributions of connected topologies to this quantity, they should also contribute to this quantity. But the interesting thing is the M goes to 0 analytic continuation. It's subtle, and it turns out something really interesting happens. So let me now talk about the free energy in JT gravity. Now I'm going to give a big picture. In my experience, there are two different types of audience members, ones who want to see the big picture and sort of snooze through the calculations, and one who wants to see the calculation. So I'm going to try to make both happy by first giving the big picture and then going into a little bit more detail. So we do find that there is a regime where replica wormholes give a larger contribution to log z than the disconnected topologies. This is a regime of low temperatures, but one where the theory is under good control. And in fact, if you just compute the annealed free energy, the disconnected topologies result in a pathological free energy. So it's clear that even if you didn't know about the replica trick, you just naively calculated log of P of B, you would find something that just does not make sense. So it's clear that's not the whole story. Now, prima facie, the pathological behavior is somewhat mitigated by the inclusion of replica wormholes, but because of technical difficulties, we can't actually tell if this is sufficient. It's not clear that including replica wormholes in a naive way is enough. And in fact, even with the inclusion of replica wormholes and a resummation of the genus expansion, the free energy appears to be non-monotonic with temperature, which is of course extremely pathological. Now, one thing that can go wrong is the analytic continuation itself. So this n goes to 0 analytic continuation. It turns out that unlike the many cases where we work with the n goes to 1 analytic continuation in the Neumann entropy, this analytic continuation has a lot of freedom, and the obvious or simple analytic continuations appear to be wrong. And I should say there are some intriguing parallels to replica symmetry breaking in spin glass systems, which similarly require a calculation of the quenched free energy that does not agree with the annealed free energy, where again, the naive analytic continuation of m goes to 0 ameliorates, but doesn't actually fix the problem. And that requires something more complicated, a multi-step replica symmetry breaking ansatz called the Parisi ansatz. I'm not going to say a lot about spin glasses because it's a parallel, it's an analogy, it's not really the same thing as what's going on here. So the main takeaway is that at least in some, was there a question?
Yeah, yes. So when you, in the previous slide, when you say pathological free energy, do you mean this pathology that it's not monotonic in temperature?
That's right. Yeah. So I'm going to, so when I finish talking about the big picture, then I'm going to talk a lot more in detail about what the pathology is, what the kind of calculation that we did is.
Okay, thanks.
Yeah. So the main takeaway, if you take away nothing else from this talk, take away this. In at least some low-dimensional theories of gravity, there exists at least one regime in which replica wormholes must make a large contribution to log z, as computed by the gravitational path integral, in order to avoid various pathologies. And this contribution appears to require a highly non-trivial analytic continuation that has some parallels with spin glasses, although I'm not going to push that analogy too far because there are also some differences. Okay, so now let me get a little bit more into the nitty-gritty of it. So here we have the JT Euclidean action with its usual topological term and the dilaton terms. And the path integral over geometries that connect M boundaries with length B was calculated by Schankar Stanford. So you can write it in this way. And here this ZG comma M. So G here is the genus. This is a function of the volume and moduli space, so-called Val-Pearson volumes, of constant negative curvatures with M boundaries and genus G. So these are polynomials of this order. And yeah, the beta here is the obvious temperature parameter. So here's just an illustrative example. So P con comma 2. So here we have this topology, and then we have higher genus corrections over here. So the connected topologies are suppressed at large S naught. And you can do a simple analysis that shows that the connected topologies can only start competing with the disks when beta to the 3/2 e to the minus S naught is approximately order 1. So you're looking at a low temperature regime here. Now, at this point, you might raise a very valid concern, which is that you appear to need the main parameter in the problem, beta, to be non-perturbatively large in S naught. So it looks like you might need non-perturbatively small temperatures. So in fact, you actually might raise two concerns. First, you could say that the connected topologies only dominate in a regime that requires non-perturbative physics. Now, I would argue this is really no different from the von Neumann entropy case, where the size of the Hilbert space of the radiation has to compete with e to the S naught. And those connected topologies we certainly were able to include in a semi-classical approximation. Now, another concern you might raise is that the genus expansion is asymptotic at low temperatures. Now, fortunately, it turns out there's actually a separation of scales. There's an intermediate regime where connected topologies can dominate, and the temperatures are not so low that the genus expansion is out of control. And on top of that, if you're still worried, in a certain limit, the so-called Airy limit, we can actually sum the genus expansion exactly and show that it doesn't qualitatively change any of the results. So, sorry, you're cut off. I can't understand.
My voice.
No, I can't understand. I mean, I'm hearing bits and pieces. Sorry about that. If you want to type it into the chat, then I can answer it. Yeah.
Okay.
Yeah, I'm going to continue talking, and when I see, I'll pause and answer. So here we have. Let's just look at the anneal free energy. What does it do? So this is computed just from the disconnected topologies, and you have to include the high genus corrections. So it turns out that this is non-monotonic in temperature. So ignore the red curve for now. I'll tell you what it is in a moment. But if you do just a partial sum analysis, then you see that this appears to be non-monotonic in temperature. Now, I'm going to say a few more words about the technical aspects of the partial sum analysis, given that this is an asymptotic series. But let me just say briefly now, because S is minus df dt, this means that there's negative entropy somewhere. And that's unphysical. So the conclusion that the free energy that's computed purely from disconnected topologies is non-monotonic in temperature is a disaster in the sense that the anneal free energy cannot possibly be the correct one. Now, let me say a bit more about the genus expansion. So this non-monotonicity, you might worry, is maybe it's not robust against higher genus corrections. And it's a somewhat complicated analysis, but you can do it really in one of two ways. You can do a partial sum analysis of the asymptotic genus expansion, or you can do a low temperature expansion and work in the Airy limit to sum the genus expansion, which is the red curve, which I'll say more about in the next slide. So these blue curves here, these are partial sums of the asymptotic genus expansion. Now, at very low temperature, this expansion is very poorly behaved, and we really should not trust that it's approximating anything that like what we actually want. But there is an intermediate low temperature regime, so starting around here, where the asymptotic series is under control, and the partial sums should be a good approximation for what the series is actually doing. And this non-monotonicity, where it goes up and then comes down again, is in this regime, which is under control. So it's not in this poorly controlled regime that we can't really say much about. Now, this is a pretty robust analysis, but if you actually are still doubtful, we can work in the area limit. So if you take S naught large and TE to the 2S naught over 3 fixed, then you can actually exchange the asymptotic genus expansion for an expansion at low temperature. And this you can sum exactly, which gives you this red curve here. And this immediately tells you, yes, this maximum up here, this non-monotonicity, is robust against adding higher genus corrections. So we're left with, yeah.
So I'm trying to understand this statement about there being a negative entropy for this monoplicity. So this is about S naught or even after adding S naught? There's a background S naught, right? Entropy or?
This is, so S naught is it's a parameter that we, I guess in principle you can take to be whatever you want. We work in the large S naught limit.
Okay, but if in the ground, so F naught is roughly the ground state entropy? Or
something that what?
It is like the ground state entropy? Or?
So S naught is coming from the, if you want to think about it in terms of dimensional reduction, it's coming from the higher dimensional black hole entropy. Does that answer your question?
Yes. I'm just asking whether, whether how sharp this contradiction is. Whether, because
how sharp, you mean how certain we are that the annealed free energy is actually pathological, is actually non-monotonic?
I'm just saying that if this argument that the entropy is negative, if it is about a background entropy, it may not be such a problem, right? Or
so I'm not 100% sure I understand what you're asking, but the free energy at any S naught should not be non-monotonic. I mean, that is a problem. And this is robust. We're working in a temperature regime where that is robust. We're not actually taking T equals 0, if that helps.
Okay. Maybe let me just rephrase one more question and then I'll stop. So if I think of this JT gravity as coming from a near horizon regime of some extremal black hole,
Mm-hmm.
Would there be a problem even in that case if you only consider disconnected topologies?
Oh, you mean if I want to go back to working in the 4D picture?
Yeah.
I haven't thought through the subtlety. Well, okay, so there's the issue of matter, which we're working with pure JT here, and I haven't thought through the subtleties. So I actually want to get back to you on that.
Okay, thanks.
Yeah.
Sorry.
So,
Ask a question.
is there another question?
Yeah. Can you hear me?
Yeah.
Okay. So isn't it the case that JT is non-perturbatively unstable in the sense that the eigenvalues can actually tunnel out of the allowed energy region in this area case? So what I'm saying is that one can think that if you take a non-perturbatively stable theory and then look at the non-perturbative effects, you might get a free energy that is well behaved.
So you can look at various different, you can think of JT as, if you want to think from the perspective of SYK, where sort of JT is approximating some sector of it, and you can think maybe JT, we shouldn't take JT seriously as a holographic theory in certain cases. We can also just say, we're looking for a simple gravitational theory where we can see this phenomenon to know if it contributes at all. And if it does, then we are certainly able to then ask the question, well, what about, you could say, more reasonable theories that maybe we can imagine their non-perturbative completion is a little bit more reasonable than that of JT. Yeah, I'm not going to say that JT gravity is a really great theory of gravity.
Okay, thank you.
Yeah. Okay, so this is meant to be as an illustration of what the gravitational path integral can do and what can go into it. An illustration that this replica trick into free energy is very important. Now, we want to compute the quenched free energy since the annealed free energy is clearly pathological. But unfortunately, we actually can't compute this thing as an analytic function of M because these ZGMs are not known as analytic functions of M. You can define them sort of iteratively, but you don't have them as analytic functions of M. So instead, what we did was define this truncated path integral P sub little m comma big M, which connects up to capital M boundaries via this iterative procedure. So let's take as an example P12 comma 4. So that means that we have 12 boundaries and up to 4 of them are connected. So we get this contribution. Then we get this contribution plus P4 comma 3, which means that we have 4 boundaries and up to 3 of them are connected, and so on and so forth. I see there's a question in the chat. Let me just try to get to it. Oh, this is from Juan, thanks. All right. So the quantity energy would be given by a double limit here. Capital M goes to infinity, little m goes to 0 of this quantity here. Now, we can't do this again for arbitrary m, but for a given fixed m, we can analytically continue to m goes to 0. So here's a plot of what happens at different values of m. So m goes to 1, and m equals 1 is literally the annealed free energy, and it has this non-monotonicity here. Now, m equals 2 is this one, and then we get to m equals 5 is this one over here. Now, the maximum does appear to be getting milder, but it's not clear whether it'll go away altogether in the m goes to infinity limit. But there's something kind of more egregious that's happening here, which is that actually I can do a totally different analytic continuation. And in this case, my choice of different analytic continuation is very qualitatively similar, but quantitatively different. So the problem here is that the analytic continuation to m goes to 0 is not unique. And so again, these are 2 different possible analytic continuations. They're qualitatively similar, but quantitatively different. Now, this is very strange. And what it means is that, well, we have to have some way of writing down the correct analytic continuation. The naive one just doesn't seem to be the correct one. So we know that if this maximum is robust in the m goes to infinity limit, which may or may not be the case, it may be that it goes away, but maybe it goes away in all possible analytic continuations. But nonetheless, it's possible that these are not correct simply because we chose the wrong analytic continuation. There is a question of how do we figure out what's the right one? So what we've learned is not only that replica wormholes have to contribute because the annealed free energy is pathological, but they also have to contribute in a very non-trivial way via some analytic continuation. And without some top-down derivation, we don't have a way of knowing what this analytic continuation is. We're just going to have to try and guess. Now, some of you might be wondering, what about Carlson's theorem? So Carlson's theorem tells you if a function is analytic for the reals, and for the positive reals, and it grows more slowly than sine pi z on the imaginary axis, no faster than e to z elsewhere in the right half plane, and it vanishes for the positive integers, then it's identically 0. Now, what is this? Why is this useful? Generally speaking, it's used to justify the uniqueness of analytic continuation in the replica trick. For the von Neumann entropy is what usually used. You can also use it for the log z replica trick. Basically, you say, suppose there are 2 different analytic continuations, and you show that the difference between them is identically 0 using Carlson's theorem. Now, this actually doesn't apply because the increase with m is super exponential, so we actually violate some of the assumptions in Carlson's theorem. The theorem doesn't apply, which explains why we actually have this non-uniqueness in the analytic continuation. Now, finding this correct analytic continuation, I would say, is clearly important for understanding the gravitational path integral better, because regardless of what it is, it's going to, whatever it actually is, whatever the behavior is, it's going to tell us something important about the type of calculation the gravitational path integral is doing. Now, a few words about spin glasses. There's sort of an intriguingly similar story in spin glasses. The annealed free energy has this non-monotonicity. So that's this red curve over here in the spin glass, in the Charrington-Kirkpatrick model. And if you include contributions from correlated replicas, which are the spin glass analog of the replica wormholes, this improves the situation. That gives you this blue curve here, but it actually doesn't resolve it entirely. As you can tell, the blue curve is still non-monotonic. And as I mentioned before, there's a resolution, the so-called Parisi ansatz. is this analytic continuation that involves a multi-step breaking of the SM replica symmetry of the problem. And I should say, so this is a very nice and intriguing analogy, but I should say there's a paper from a couple of days ago by Clifford Johnson that suggests that you actually don't need replica symmetry breaking, but you need to include some highly non-perturbative effects that might remove the need for this this replica symmetry breaking. And I haven't fully digested the paper yet, but potentially maybe it could tell us more about what the right analytic continuation is. I would be remiss not to mention some some studies of low energy effective field theory of SYK, which have found replica symmetry breaking, but it's potentially a different sector. So it's not immediately obvious what, if any, is the connection, but there potentially is a connection there. Okay, so let me summarize here. So
can I ask a question?
Yeah.
So should I interpret your previous result on the previous transparency as saying that in the regime that you can resum the perturbation theory, there is no problem, but perhaps beyond that regime, there is a problem? So maybe
I think maybe let me go to the slide. So it here.
No, not here.
Oh.
The
this one.
The next transparency.
This one.
So yeah, because if I understand correctly, for very small t, you need some resummation of the genus expansion that cannot be done, right? For sufficiently small ones.
So if we work in the area limit, we can actually do the summation exactly.
Okay.
As long as
so
we're working.
This problem is arising already in the area limit where you can do the resummation.
Yeah, so it arises even in the area limit where we can do the summation. Okay. The problem is robust against the genus expansion. What I would say is potentially, but I would say it's potentially not robust against this m goes to infinity limit. So in this over here, so we did it up to m equals 5. So m here is the number of boundaries that we can connect. So this is a path integral for little m boundaries, but m of them are connected, capital M are connected. And I would say that the one thing which we're not sure about, whether it's robust or not, is if this non-monotonicity remains when we take big M to infinity. But we can do the summation exactly in the area limit or this low temperature limit of the genus expansion. Okay, so the overview. Sorry, does that answer your question, Juan?
Thank you.
Yeah. So some overview. So the recent developments on the black hole information paradox front have suggested that Euclidean wormholes really should be included in the gravitational path integral. And one way of interpreting this, not the only one, but certainly one, is that the gravitational path integral computes an ensemble average. Now, ultimately, we'd like to understand how general this statement is and whether it's true, or how do we understand that better, especially in higher dimensions, or n equals 4 super Young Mills, and the usual type of correspondence we like to think about. Now, I would say the gravitational path integral has been something that's been very interesting and knows in some sense a lot more than it has any right to know. We've known that for a long time. And these new developments have sort of sharpened the idea that we'd like to know how to calculate everything that the gravitational path integral calculates without using the gravitational path integral. So we'd like to calculate, say, the von Neumann entropy of the radiation without using the gravitational path integral so that we know better what the gravitational path integral is doing. So all of this means we have to understand it better. So a summary of what we did. So here we were interested in probing the replica wormhole phenomenon in the gravitational path integral by looking at a quantity which you might say is more primitive than the von Neumann entropy. It's just log z. And in JT gravity, pure JT, we find that at sufficiently low temperatures, but not so low that the genus expansion is out of control, or even at very low temperatures in the area limit, the free energy without replica wormholes is severely pathological. Now, of course, it's also pathological with replica wormholes, mildly less pathological, but unphysical is unphysical. And so this seems to be very similar to spin glasses, where a novel analytic continuation removes the pathologies altogether. Now, regardless of whether there is a parallel to spin glasses or not, it seems clear that we don't understand how to analytically continue this because there's so much freedom in how we can do so. So there has to be some other ingredient that comes in to tell us what is the correct way to analytically continue this gravitational path integral for log z, or this big path integral for log z. So some outlook. So figuring out the correct analytic continuation, again, seems very important. I should say that the analogy with spin glass, it's just an analogy and it's a loose one. It's not sufficiently informative at the JT level. We can't just come up with an analog of the Parisi ansatz for JT, because in JT gravity, we worked with the full path integral, and in spin glasses, we work in a saddle point approximation. So this saddle point approximation is pretty critical for the structure of the Parisi ansatz, and in general for the way things work with spin glasses. So this is why I'm hesitant to call this a full-fledged or analogy rather than just some kind of a loose inspiration. So if we do want to probe this a little bit further to try to get the analytic continuation to be very similar to the Parisi ansatz or get more insight out of the spin glass analogy, seems like we would need a more complicated theory of gravity where the saddle point approximation is non-trivial. So I'm going to push the spin glass analogy to a breaking point. I haven't discussed spin glasses at all, so feel free to ignore this if you feel like this is kind of stretching it. But there is a suggestion that the metric would be emergent as a consequence of ensemble averaging if we just are somewhat inspired by spin glasses. So it's emergent in some sense is a mean field. So as a very far-fetched sort of just a speculative question, is this informative in any way about space-time or geometry emergence in terms of ensemble averaging? And finally, potentially most importantly, are there any other regimes, any other theories of gravity where we can do a calculation explicitly where replica wormholes dominate the free energy, or at least where we can see a pathology in the annealed free energy? So with that, I'm going to stop. Thank you for your attention.
Well, thanks, Netta, and maybe we can clap and then we can take questions. Any questions for Netta?
Am I audible?
Yes, Shane.
Hello.
Shane, can you hear me? Can you just ask your
Yes,
question?
so, so is my voice breaking?
No.
Right now it's good.
Yeah.
Okay. I'm audible clearly, no? Okay.
Yes, please.
So, yeah. Am I audible clearly?
Yes. Maybe.
Okay. Okay, so I just had a question related to page curve. So page curve is assumed to be true for a system which is in some local QFT. What we are doing here is computing the page curve for I guess a semi-classical observer. But Hawking radiation has non-local effects due to presence of islands, and it also has features like state dependence. So is it necessary that a semi-classical observer should observe the page curve of Hawking radiation? Because it doesn't seem to be like a local QFT setup.
So I don't know what you mean by saying that the page curve is assumed for a local quantum field theory. The page curve has to be derived rather than assumed. It's a consequence of unitarity. I would say that I think that this is a personal opinion, and I think you'll find that some people might disagree with me, but I would say that for us to conclude that a system is conserving information, then you have to be able to use purely effective field theory techniques far away from the black hole when you collect the radiation to compute a unitary page curve. That would be my opinion.
I'm just confused with why local effective theory technique should work for something which is not in that setup.
When you collect the radiation at infinity, there's no reason that you would not be able to use effective field theory to compute it. I mean, you could say that maybe what you would need to actually calculate to see unitarity is something non-perturbative, but that I would say that that's something that
Hello?
yeah, sorry, can you hear me?
state dependence and non-locality in Hawking radiation.
So Netta, I think can I try maybe, because I think I might understand where the confusion is.
Yeah, sorry, this is, yeah, okay, go ahead.
Yeah, sorry.
Shreyans,
I think the point is that, you know, these derivations of the page curve involve some system which has a well-defined non-gravitational dual coupled to another non-gravitational system. So if you just look at a boundary perspective, you have one non-gravitational system coupled to another non-gravitational system, and so you clearly expect a page curve. You know, that's just a local quantum field theory. So if you just wanted to define this page curve, you could just define it completely independent of gravity. And in fact, I mean, that's important in all of these derivations. There's a non-gravitational system coupled to a system which has a gravitational dual, but which also has a non-gravitational description. So there's a clear factorization of the Hilbert space.
I would just add that the gravitational dual is something that was specific to this calculation, but the page curve does not require. The page curve is not something that was initially calculated assuming holography or assuming the existence of a gravitational dual.
There could be some, I just wanted to say that, so because I don't know why replica trick is giving us the page curve.
You don't know why what?
I don't know why replica trick is giving us the page curve. I don't know the intuition behind it. Meaning it's some stronger version of semi-classical calculation, but a generic setup would have required a microscopic theory of gravity, but somehow replica trick is producing the page curve. So I don't know the intuition for why this trick seems to be working so fruitfully.
I'm not sure exactly what you're asking. I mean, so if your question is whether you would need non-perturbative quantum gravity or access to non-perturbative physics as an asymptotic observer in order to look at the Hawking radiation and find that it's unitary, or if if that's your question, I would say that I don't think we've answered that, because what we've answered so far is not in terms of the perspective of an observer outside the black hole. It's a calculation of the entropy that's been done. That's well, it assumes access to the entire state in a sense. So, I mean, maybe I'm not understanding what you're asking exactly, but I would say that it's not obvious to me what the answer is.
Okay, thank you.
Shrideep, you have a question? Okay. Are there any other questions? Netta?
Can I ask more questions?
Maybe we can give opportunities for other people, and if there are no other questions, then yeah, we can continue. So
thank you.
Yeah.
Can I ask a question? I have a question.
Okay.
Good night. Hi.
Yes, please, Fenta, go ahead.
Okay. Yeah. Hi. You mentioned, Netta, that there is a study of the SYK model by Arafieva and collaborators in which the non-diagonal saddle point seems to be important.
Yeah.
Yeah. So I wonder what is the implication of this type of result. I have not read this paper yet, but for the standard way in which we treat the SYK model in the large n limit and the low energy limit, in which replica symmetry breaking doesn't seem to be there.
Yeah. Mm-hmm.
And in fact, the quenched and the annealed problems are almost identical, in fact. So you have a comment on this?
So my understanding of what they do is that the low energy limit that they consider is not the one. It's not really SYK. So it's I mean, it doesn't have the same type of UV completion. So my understanding is that there's no inconsistency with the usual analysis, which finds that there is no spin glass phase and there are no replica wormholes contributing. And this is one of the reasons I mentioned it, is because it seems that it's potentially analogous to this pure JT picture, which only looks like SYK in certain cases.
I see. Okay, thank you. Thanks.
So, Ali Siraj.
Yes, hello. So can you go to the beginning of your talk where you define the log of z as the limit of m to 0?
Yeah, give me 1 second. Wait, I think I just had it. Okay, not quite. Yeah.
Yes, so the first line, the first equality is some mathematical equality, right? So this is the way, I mean, both sides of the equation have a meaning, and this is a way to compute the log of z.
Yeah.
But the second line, I mean, is it a definition that you do, or what is this? Is it the same like the first one?
So the second line is a statement: if you want to compute log z from the gravitational path integral in a way that's parallel to how we compute the von Neumann entropy from the gravitational path integral, then you would want to replace z with p, and that would and this overline here, you could say it's a definition. This overline here is what defines the free energy as computed by the gravitational path integral.
Right. I mean, does the left-hand side have a meaning in its own, or the right-hand side is what defines the left-hand side?
So good. So in a theory where you know the kind of ensemble averaging which is being done, then the left-hand side does have a meaning on its own. So you could say, okay, this is some kind of a, can we go up a couple of slides? So for example, in a theory where you have this type of formula where you know what the overbar means in terms of some averaging over a distribution, then you could say, okay, I know what that means. In gravity, we have a bit more of a problem because we actually don't know if the gravitational path integral is computing an ensemble or what kind of ensemble it's computing. So in that case, this is more of it's really a question: how do we define this? How do we compute this without invoking the replica trick? If we knew what kind of ensemble averaging it's doing, we would be able to do that.
Yes, because at the end you show that the right-hand side is not very well defined. I mean, it's pathological, right? It doesn't have the right behavior.
The right-hand side, so the problem, of course, is that this limit as m goes to 0 is kind of a loaded, it's a loaded thing. So it means that there is an analytic continuation of as m goes to 0 that makes, for example, at this level, there is an analytic continuation as m goes to 0 that makes this true. And in particular, that what this means is that for whatever is the right quantity here, whatever is this, let's say ensemble averaging, which is done correctly, there exists a limit. This is an analytic continuation of m goes to 0 that also computes it correctly. So the problem is that we don't actually have a top-down derivation of what that is.
Right. So you say that the only problem could arise from this freedom in the analytic continuation, not from the rest of the equation. I mean,
that's right. Yeah.
Can I think about another way to define the left-hand side, or no?
So the left-hand side, I would, again, if you want to sort of buy into the idea that the gravitational path integral is definitely computing on ensemble average, you would say the left-hand side is the ensemble average of log z in quantum gravity. The problem is not that it's not, we could say it's not that it's not well defined, it's just we don't know how to compute it otherwise.
Right.
Just a quick comment. Just a quick comment, I'm sorry. P, V of M in the second hand side are all sets of topologies which are not disconnected.
So P of B to the M includes all, so this is just the path integral on B to the M, which includes both connected and disconnected topologies. So it can be dominated completely by the disconnected topologies, in which case it's quite simple, but it also, in certain cases, is not.
What's the difference between Z and P?
So Z is the partition function, and P is the gravitational path integral.
Okay, okay. Okay, so yeah, I got it. And instead of, so we have replaced 1 minus n by some variable m.
Sorry, could you just repeat that? You were cut off for a second.
Yeah. We have replaced 1 minus n, where we analytically continue in n to m.
We have not replaced anything. This is the formula as it currently stands.
I thought it is 1 upon 1 minus n zbn minus zb raised to power n.
So I think maybe, are you thinking of the von Neumann entropy replica trick? That's a distinct replica trick, which is different from this one. That one has 1 minus n in it, but we haven't replaced anything in that one. This is a new replica trick. Well, new. I mean, it's been known for many decades. We didn't invent it, but it's new in the sense of it's not the same as the von Neumann entropy replica trick. So maybe, I mean, maybe you're referring to to this, where we have to do both. So this is a situation where we compute the von Neumann entropy from the gravitational path integral, and we have to do both replica tricks. So here we have both 1 over 1 minus n, n goes to 1, and m goes to 0 limit.
So why do we need a new replica trick? Is it because the setup doesn't seem to be giving us the page curve using the old replica trick?
No, the page curve has nothing to do with this. The reason we need the second replica trick is because this log z of b, let me go up here, because these two are fundamentally two different objects. So log of p of b is not the same as this averaged log of b, the average log of z of b. So these two are two different quantities, and in order to do the calculation correctly, we have to include this one. This is why we're doing this. You don't need the page curve in order to see that this matters. So here's an example where you just calculate the von Neumann entropy of a pure state, and you find that if you don't include this additional replica trick, you can get subleading terms that are not exactly 0.
Oh, okay, okay. Thank you. So where does this trick come from?
Sorry, maybe Shreyans, we can see if somebody else has questions, and then
I'm sorry.
to this. Yeah. So Shabi.
Hi. So I just wanted to ask, so while calculating this average of log of z, you said that this is, there are some examples in condensed matter which has been considered, and especially for the spin glass cases, you have this Parisi ansatz. So in those cases, I mean, with this m going to 0 limit, I guess, has been successfully taken. So could you please tell a little bit about what is the rationale behind doing the correct analytic continuation in those cases? How does one figure out what is the correct one?
Right, so the celebrated Parisi ansatz, which, it's a multi-step replica symmetry breaking, in the sense that it breaks the SM, so S here, the permutation group, it breaks the SM replica symmetry in a particular way. We would like to get inspiration from that for gravity. The problem is that it's fundamentally a saddle point analysis. So it essentially looks at the saddles and it assigns certain, it's a saddle point analysis. And the way that we did the JT gravity calculation, we just did a full path integral. So it's very difficult to push the analogy to the point where we can get something out of the intuition behind the Parisi ansatz. What we're looking into right now with Sebastian and Alex, one thing we're looking into right now is finding a situation where we can actually do a saddle point analysis, which is non-trivial, where the saddles are non-trivial, and see if we can mimic the Parisi ansatz in that setting where it's easier to draw the parallel with spin glasses.
Okay, so just one more thing is that even in the saddle point approximation, there is still an ambiguity of taking the m going to 0 limit, and there is a way to fix. Okay.
Yeah, okay. I don't know about gravity because we haven't done that calculation, but at least in spin glasses, there's a non-uniqueness in the m goes to 0 limit, even in the saddle point approximation.
Okay, okay, thank you. Okay.
Hamid?
Yes. My question about the saddle point comment that you made. If I understand correctly, these wormholes are not the real saddles of the theory, right? Then how would you expect to change?
The wormholes,
I mean,
repeat that last sentence. The wormholes are not what?
are not the saddle points of the theory.
So they should be. In JT gravity, we just work with the full path integral because the saddle points are boring. But we're looking for a. You could imagine working, for example, in a 3D theory where you literally have solutions to the Einstein equation, maybe 3D pure gravity. Maybe you have solutions to the Einstein equation that are these replica wormholes. So in fact, there was a recent paper. I'm blanking actually. I thought there was a recent paper that had an explicit saddle point solution in some theory of gravity, some non-trivial theory of gravity with a replica wormhole. So we would expect that, but we would want to work in a theory where we can actually see the saddle point. You can see these replica wormholes as saddle points. In this this m goes to 0 in the free energy replica trick.
I see. Thanks.
So, is there anybody else who wants to ask questions?
Can I ask a question?
Okay, maybe I can ask a bunch of questions and then I will leave. But okay, so one of the things that so Netta, I just had a few questions, so one is about like this this negativity in the entropy.
Yeah.
In the computation of log z, is there a way of stating that in terms of some correlation function? Like I can in principle kind of differentiate the log z with respect to some sources and get some correlation functions. Is there a statement also at the level of correlation functions about some correlation function which you expect to be positive but it is not?
That's a really good question, and I think probably a really good calculation to do, what we haven't done. I would expect that, or I would hope that signatures, that if you use the wrong log z, that the signature of that pathology would propagate into other observables in the theory. So I think, I haven't done the calculation, but I think it would be a really interesting one to do.
Okay, for example, like if we calculate the energy, which might be something easier to calculate, is energy ever negative? Or,
sorry, you calculate the free energy analytically?
Yes, expectation value of energy.
So yeah, hang on, let me just go to this slide. So actually, let me say something different. So if you're willing to work with something like CGHS, so I just talked about JT gravity, but we actually did a calculation in a simplified version of CGHS where you can do everything analytically. You still have the problem with the m goes to 0 limit. There's still a problem with the analytic continuation, but there we don't run into the issues. So let me quickly go here. So yeah, so here the problem is we have to take this limit that we don't know how to do analytically because the Val-Peterson volumes are not known analytically. So what we have to do instead is we just plot a bunch of m's. For any given m, we can compute this analytically. But if you want to actually have, an analytic formula that's actually complete, that has the m goes to infinity limit, we don't know how to do that. But if you wanted to just see what signatures in other observables you might get that are sick, one thing you could do is work with the simplified version of CGHS, where we can actually do this calculation we did in the paper. And there, you really just have, you actually just have two topologies contributing. So you have the disconnected topology and the topology that connects two boundaries. And there you can do everything analytically. And you could imagine testing these, you can imagine computing correlation functions in that theory.
Okay, thanks. So just one more question. So this is regarding the statement that there is an ambiguity in analytic continuation. And perhaps, so does that mean there are some highly non-perturbative things that we are missing in this JT gravity path integral? And if so, like how is this consistent with this other statement that sometimes, these things about ramps and so on and so forth, ramps and plateaus, you can get it from JT gravity. I mean, we do, yeah.
So I should say, I should mention Clifford's paper here. So again, it's a very recent paper, and I haven't digested it yet, so I don't want to assert too much about what he does there. But he has it appears that there are some very, very non-perturbative effects that that can come in to remove the need for replica symmetry breaking, but they do not fix the annealed free energy, because that one we can calculate exactly in the area limit. So they can, it's potentially, it removes the need for replica symmetry breaking, although it's not entirely clear what that means, because it still doesn't tell us, and again, I haven't read the paper in very careful detail yet, but it doesn't tell us what the, as far as I understand it, it doesn't immediately obviously tell us what the correct m goes to 0 limit is in this replica trick. There appears to be a different way of calculating the free energy.
Okay, thanks. Any other questions?
Can I ask a question?
Yeah, sure. Please go ahead.
Okay. Thank you. So, maybe it's a slightly tangential question. It might not be related with the paper. We know about islands topology being dynamical, but these topologies seem to be coming from the gravity path integral. I just wanted to get some intuition as to why these topologies are dynamical, meaning if it's just from gravity path integral, what is causing these geometries to be dynamical? Meaning it's changing as a function of time. It becomes significant after the page time, but if we just see the setup, then these topologies seem to be dynamical, whether it's page time or not. So why is that so?
So again, this is quite besides the point of the talk, but the calculations of the replica wormholes are done in Euclidean signature. So you can sort of mimic the evaporation of the, you can sort of try to mimic the black hole evaporation picture. I would recommend that you look at the West Coast and East Coast papers, where, for example, in the West Coast paper, they look at the states on the end of the world brane. And in the East Coast paper, they look at this regions R. And but the calculation is done purely in Euclidean signature. So in other words, it's a stationary calculation. You change parameters.
If I consider the calculation in the Lorentzian picture, was what is causing the geometries to become dynamical?
I don't. Please correct me if I'm wrong, but I don't believe the calculation has been done in the Lorentzian picture at this point.
Okay. Okay, I got it. And do we require an ensemble interpretation for a single unitary theory?
Sorry, will we require an ensemble interpretation for what?
Single unitary theory like n equals 4 Yang-Mills theory.
Well, I think that's up in the air. What is the, I mean, it was one of the open questions I put down. What is the, how do we interpret the potential ensemble interpretation of the gravitational path integral if we're working with n equals 4 Yang-Mills? Again, nobody's proven that the ensemble interpretation is the correct one.
Thank you.
Okay, are there any other questions? So, Hamid, did you have more questions or?
Yeah, very quick question. So the where you had this averaging over log of z somehow with the weight a p of g, I guess, something like in the I think in the slide first few slides. You had an average of log of z, I guess.
I'm just going to try to find the slide you're talking about. So are you talking about this or something earlier?
No, no, no. Earlier.
Earlier.
Yeah, even earlier.
Earlier, okay. This?
Yes, exactly. So
yeah.
if I want to, I mean, if one would extrapolate this for log of z also somehow, then would that mean that somehow this p of g as a weight, I mean, for different topologies, is somehow working differently? I mean, in principle, I could come up with some weights that would weight different topologies differently, such that I get a monotonic answer. Is that right?
Well, the problem is that we don't know what z sub g of b is. Right? If z overline is of b, that's what's computed by a gravitational path integral. We don't know what the individual constituents in the ensemble are. I think the problem is worse than finding what the distribution is. It's finding what the individual z sub g of b are. I don't think we have a good understanding of what that is, if in fact this is the correct interpretation of the gravitational path integral.
Okay, thanks.
Are there any other questions, comments?
Just a last question, if it's okay.
Yeah.
Okay, so why is it that in the low temperature limit, higher genus contribution become more dominant?
So it's because JT gravity has this topological term, which is essentially weighted by. I'm not going to bother going to this slide. The topological term is essentially weighted by this this S naught term. So so that means that it's weighted. Actually, let me actually go to it. There we go. Okay, so if you want to, yeah, actually, you can look at this term right here. So these are, this is essentially what tells you which contributions come in with what weight. And if you just look at this and stare at it for a little bit, you'll see that there's I mean, these are polynomials in beta. This is an e to the minus s naught term.
I'm sorry, there is some connection problem.
So it's just I mean, it's just a matter of looking at this formula. It's just a balancing out of the beta versus e to the minus s naught, and the s naught comes in because there's a topological term over here. So that's why the reason that s naught controls the topologies is because this is a topological term, and it's balanced out by polynomials of order beta of the polynomials in beta.
Okay, so as beta increases, zg of m also increases.
Sorry, what was that?
As zgm increases, sorry, as beta increases, zg comma m also increases.
Yes,
That's
I mean,
why higher genus.
Yeah, so higher genus is going to be suppressed if you have. I mean, so here I think I have. Yeah, so this. It's just. I mean, it's just an analysis of this thing. That's what. That's the number you get from that.
Okay. Okay. Thank you.
Okay. Any other questions, comments, and so on. Okay, if there are no further questions, let's thank Netta again for this nice talk, and yeah, and see you guys on Friday for the next seminar. Okay. Okay, so Netta, thanks, and so I'll just disconnect, and yeah, thanks a lot for